Welcome! In this video, we shall introduce the concept of linear independence. It describes whether or not any vector in a sequence can be produced by other vectors in that sequence. Let's review the term linear combination. Let V1 up to Vn be vectors in a vector space. A linear combination of V1 up to Vn is the expression formed by summing all the scalar multiples of these vectors. We notice that this expression gives us a vector in the vector space. For example, we have vectors V1, V2, and V3 in R3. Since we can write V3 as 3 times V1 plus V2, we say that V3 can be expressed as a linear combination of V1 and V2. Geometrically, whatever position that V3 can reach can also be reached by 3 times V1 plus V2. This means we can replace V3 by 3V1 plus V2 to do the same job. Next, we have vectors A1, A2, and A3 in R3. This is a linear combination of A1 and A2. However, no matter what scalars we apply, we cannot get a 5 here, so we can never obtain A3. Similarly, for the linear combination of A2 and A3, no matter what scalars we apply, the first two entries will be the same, so we can't obtain A1. Finally, no matter what scalars we apply to form a linear combination of A1 and A3, we can't get a 3 here, so we can't obtain A2. As a result, none of the vectors can be expressed as a linear combination of the other two vectors. Geometrically, we cannot reach the same position that a vector can reach by using the other two vectors. This means we cannot use other vectors to take over the job that any individual vector does. We can see that in illustration 1, we can use other vectors to replace a vector to do the same job, whereas in illustration 2, we cannot use other vectors to take over the job that any individual vector does. This property distinguishes these two sequences of vectors and brings the concept of linear independence. Here's the definition. Let V be a vector space. A sequence of vectors V1 up to Vn in V is linearly dependent if at least one of the vectors can be expressed as a linear combination of the others. Otherwise, it is linearly independent. In our situation, the vectors from illustration 1 are linearly dependent, whereas the vectors from illustration 2 are linearly independent. In fact, we can also relate the vectors with the zero vector. For illustration 1, we can rewrite this equation as 3 times V1 plus V2 minus V3 equals the zero vector, or other possible ways. If a helicam is programmed to move towards the same or opposite direction as the first vector, the second vector, and the third vector in this order, then there are paths that the helicam leaves the origin and returns again. What about the vectors from illustration 2? How do we express the zero vector as a linear combination of A1, A2, and A3? We solve this vector equation for the scalars K1, K2, and K3. It turns out that K1, K2, and K3 must be all zero. It means if the helicam leaves the origin, we must pick it as somewhere else. We are actually referring to an equivalence definition of linear independence, as stated here. Let V be a vector space. A sequence of vectors v1 up to vn in V is linearly independent if and only if the only scalars satisfying this vector equation is to have all the scalars k1 up to kn equal to 0.